a particle moves along the curve xy equals 16 so that the y coordinate is increasing. Let me underline this. The y coordinate is increasing at a constant rate of 2 units per minute. That means that the rate of change of y with respect to t is equal to 2. What is the magnitude in units per minute of the particle's velocity vector when the particle is at the point 4, 4? So when x is 4 and y is 4. So let's see what's going on. So let's first just remind ourselves what the velocity vector will look like. So our velocity is going to be a function of time, and it's going to have two components. It's going to be what is the rate of change in the x direction and the rate of change in the y direction. So the rate of change in the x direction is going to be dx dt, and the rate of change in the y direction is going to be dy dt. And they tell us that that dy dt is a constant 2 units per minute. But they're not even just asking us for just the velocity vector for its components. They're asking for the magnitude. They're asking for the magnitude of the particle's velocity vector. Well, if I have some vector, let me do a little bit of an aside here. If I have some vector, let's say a, that has components, I don't know, b and c, well, then the magnitude of my vector, sometimes you'll see it written like that. Sometimes you'll see it written with double bars like that. The magnitude of my vector, and this comes straight out of the Pythagorean theorem, this is going to be the square root of b squared plus c squared. The square root of the x component squared plus the y component squared. So if we want to know the magnitude of our velocity vector, the magnitude of the particle's velocity vector, well, I could write that as the magnitude of v, and I could even write it as a function of t. It's going to be equal to the square root of the x component squared. So that's the rate of change of x with respect to time squared plus the y component squared, which in this case is the rate of change of y with respect to t squared. So how do we figure out these two things? Well, we already know the rate of change of y with respect to t. They say that's a constant rate of 2 units per minute. So we already know that this is going to be 2, or that this whole thing right over here is going to be 4. But how do we figure out the rate of change of x with respect to t? Well, we could take our original equation that describes the curve. We could take the derivative of both sides with respect to t, and then that's going to give us an equation that involves x, y, and dx dt and dy dt. So let's do that. So we have x, y is equal to 16. I'm going to take the derivative with respect to t of both sides. Let me do that in a different color, just for a little bit of variety. So derivative with respect to t of the left-hand side, derivative with respect to t of the right-hand side. On the left-hand side, if we view this as the product of two functions, if we say, look, x is a function of t and y is also a function of t, we're going to do a little bit of the product rule and a little bit of the chain rule here. And so this is going to be equal to derivative of the first function, which is, so we'll first say the derivative of x with respect to x is 1 times the derivative of x with respect to t. Remember, we're taking the derivative with respect to t, not with respect to x, times the second function. So times the second function. So times y. So times y plus the first function, which is just x, times the derivative of the second function with respect to t. So first, what's the derivative of y with respect to y? Well, that's just 1. And then what's the derivative of y with respect to t? Well, that's dy dt. And that is going to be equal to, the derivative of a constant is just 0. So let's see, what does this simplify to? This simplifies to, in fact, we don't even have to simplify it more. We can actually plug in the values to solve for dx dt. We know that dy dt is a constant 2. And we want the magnitude of the particle's velocity vector when the particle is at the point 4, 4. So when x is equal to 4, and y is equal to 4, and y is equal to 4. So now, it's a little messy right now, but this right here is an equation that we can solve for. There's only one unknown here, the rate of change of x with respect to t, right when we are at the point 4, 4. And so if we're able to figure that out, we could substitute that in here and figure out the magnitude of our velocity vector. So let us write it out. So this gives us 4 dx dt plus, what is this, 4 times 2 plus 8 is equal to 0. And so we have 4 dx dt is equal to negative 8. Just subtracted 8 from both sides. Divide both sides by 4. You get dx dt, let me scroll down, is equal to negative 2. So when all this stuff is going on, the rate of change of x with respect to t is negative 2. And so then when you square it, you get a 4 right over here. And so the magnitude of our velocity vector is going to be equal to the square root of 4 plus 4, which is equal to 8, which is the same thing as 4 times 2. So this is going to be 2 square roots of 2 units per minute. So that's the magnitude of the velocity vector.